everyone, welcome to lecture 3.2. Today you'll need these things before you get started. The first thing that I want to talk about today is the whole concept of comparing different solutions. This should be something of particular interest to you all as nurses because it's a concept that you have to run into on an almost daily basis. Okay. So what we're going to be doing is comparing the relative concentrations of two different solutions. You're always going to be comparing them in reference to what we call the comparing solution. In medicine, the comparing solution is usually your blood or your blood cells. Okay, so let's talk about what each of these three terms means. A hypertonic solution is one that has a higher concentration of solute than the comparing solution. The isotonic solution is one that has the exact same concentration of solute as your comparing solution. And then your hypotonic solution is the one that has a lower concentration of solute than your comparing solution. Keep these definitions handy. The words in and of themselves are self-explanatory. Hyper means more, hypo means less. If you have hypertension, that means that you have too high of blood pressure. Hypotension, on the other hand, means that your blood pressure is too low. Iso is the word that's used to refer to things that are the same. Okay, so let's talk about this in real terms. If the concentration of NaCl in the blood is 0.9%, now, before we move on, I just wanted to make a note of this because I'm going to be using this notation now from now on. These brackets here, these square-shaped brackets, that's chemistry word for concentration of. So if you see the word glucose in those square brackets, that means the concentration of glucose. Okay, so let's say that we have a salt concentration of 0.9% in your RBCs. Okay, so let's determine what type of solution each one of these examples is. If you have 5.0%, is that bigger or smaller or the same as 0.9? It's bigger. So this is your hypertonic solution. What about 0.9? Remember, we're always comparing these new solutions to our comparing solution, which is this value here. So in this case, the 0.9 is the isotonic solution. They have to be exactly the same. 0.8 is not exactly the same as 0.9. And then we have a solution of 0.1% sodium chloride. That's hypotonic. It has a smaller concentration of sodium chloride than what is in your blood. So why does it matter? Well, if you have a patient that is dehydrated, it's very important that you not give him or her a hyper or a hypotonic solution in an IV. That's why when you have maintenance IV bags, or if you have a patient that's coming in to treat them for dehydration, you're not going to give them something that's a 5% glucose solution. That is going to dehydrate the person. Yes, that will add sugar to their blood, but if you have somebody who's suffering from dehydration, you have to give them a comparable isotonic solution. A lot of times you'll see this terminology when you're looking at saline or contact solution. It's very important to have an isotonic solution that you're putting in your eyes because that's a very watery environment and it has to stay that way. We'll talk a little bit about why this is all important when we get to osmotic pressure in a little bit. But I wanted to define these terms at the outset. far we've only been looking at solutions and comparing them if they're in percent already, if that's the concentration. If these solutions are not in percent, and in chemistry you won't see them in percent, you'll see them in molar or capital M. If that's the case, you must calculate the osmolarity for both solutions. Otherwise, you're going to be comparing apples to oranges. Okay, so let's calculate the osmolarity of this, which is, I'm just calling my comparing solution. How many particles does glucose have? 1. So this has an osmolarity of 0.30. Okay, let's calculate the osmolarity of 0.10 molar NaCl. I have 2 particles here, so my osmolarity will be 0.20. And now this is why we have to compare osmolarities. It doesn't matter what the identity of your solution is. It just matters how much solute is in it. And the only way to determine how much solute is present is by calculating the osmolarity. So that's why we always have to compare osmolarities with each other. So here we have 0.20 osmoles and we have 0.30 osmoles for the glucose. Is this solution hypo, hyper, or isotonic to this solution? This is the smaller number. That means that this has to be the hypotonic solution. Okay, let's calculate the osmolarity for this formula. We have 1 magnesium and 2 bromines, so therefore we have 3 particles. 3 times 0.1 is 0.3. 0.30 OSM, magnesium bromide. Now compare these 2 solutions. Are they hypo, hyper, or isotonic? This would be an isotonic solution because they're the same. Now if you're asked to identify those solutions, if it's in percent, you can leave it in percent. If it is in molarity, you must calculate osmolarity. Okay, let's talk a little bit about the colligative properties. Now the colligative properties are something I need you to know a little bit about. And the thing that I want you to know is the definition of each property and its real-world application. Colligative. No, it's not named for Caligula. Colligative is in reference to how something is changing once you are changing its state. So here we're changing something from a solvent to a solution, from a solvent to a solution. So a colligative property then is a property of a solvent, so we're just starting out with a solvent, that changes when any solute is added. So in other words, these colligative properties are these new properties that you get when you go from just pure solvent to a solution. So if you need a picture, here you have a beaker of just water. Now you have a beaker of water with solute in it. This will become really obvious as we work through these examples. Okay, the first colligative property is called freezing point depression. This property states that the freezing point, which is the same thing as melting point, depending on your perspective. The freezing point of a solvent decreases after solute is added. So this is the definition I need you to know. When you add a solute to a solvent, its freezing point falls. It becomes a a smaller number, or more negative. The best example of freezing point depression is ice melt. Okay, so we all live in Wisconsin. What do you do when your driveway gets slippery in the wintertime? You put ice melt on it, right? Ice melt is basically just salt. And what it does is, when the salt combines with the frozen water, the ice on your driveway, it forms a solution. So you're going from pure solvent to solution. And in this case, your pure solvent is the ice on the driveway. And the solution is the water plus the salt on your driveway. Okay, so why does that work? Why is ice melt something you should have in your garage? Well, the freezing point or the melting point of water is what? Well, we know it as 32 degrees Fahrenheit, but in chemistry land we like to use Celsius. So here we have 0 degrees Celsius. I think I'll actually we'll use both of them. It's easier for us to think about it in terms of Fahrenheit. When you add the ice melt and you make a solution on your driveway, what you're actually doing is decreasing the melting point of the water. So now the melting point of this solution is somewhere around 23 degrees Fahrenheit, or about 10 degrees Celsius. These are not exact numbers. It depends on how much you put on, and it depends on other conditions as well, but don't worry about that. Okay, so what you're doing here is you're taking your ice from melting at 32 degrees to melting at 23 degrees. If you have conditions where the ambient temperature is below 23 degrees, or your driveway's, the actual temperature of your driveway's concrete is below 23 degrees Fahrenheit, your ice melt will not work. The only way that it can work is up until you have about 22 or 23 degrees Fahrenheit. That's as far down as you can go and still have the water melt. Ice melt is also good for providing some traction by increasing the surface area of your driving surface. So it's something for your tires to grip onto. So that's why it is also purposeful if it's below that temperature. Now, curiously, when we're talking about colligative properties, the identity of the solute being added to your solution is of no consequence. It doesn't matter what kind of salt you have in the ice melt or what brand you buy, they all work the same way if it has the same concentration. In fact, a couple of winters ago in Green Bay, this was, I want to say, like in maybe 08 or 09, there was a really bad winter, and it was so bad that all of the salt stores ran out. And so the city didn't have any salt, and it's really expensive to buy salt from other municipalities and to have it shipped in. So instead of using salt, they used beet juice. Well, it has the same concentration of salts in the beet juice, and so it was able to melt the ice on the roadways. Well, a lot of folks complained, especially if they had white cars or white shoes or something, because beet juice does stain a little bit. So it was a little bit controversial, but it worked, and it saved probably a few accidents from occurring on the roadways. So the moral of the story is that beet juice and ice melt work the same way. So if you run out of ice melt, you can always boil up a couple of beets and spread that on your driveway if you feel inclined. So, colligative properties, the identity of the solute is of no consequence. The second colligative property is known as boiling point elevation. This this means that the boiling point of a pure solvent will increase if solute is added. The boiling point of your solvent will increase if you add a solute. The most common example of this is when you add salt to your water to, I'm going to put this in quotation marks, make it boil faster. So how many of you do this? Let's say you're making macaroni and cheese, or you're making spaghetti, or you're making lasagna and you need to soften the noodles. You put your water in your pot, put that on the stove, and you sprinkle a little salt in because you think, oh, my mom always told me that I should add salt to make the water boil faster. That is not true. When you add the salt, you're actually increasing the boiling point of the water. Okay, so let's say you have one of those fancy cook kettles where you can see through it. Here you just have water. Water has a boiling point of 100 degrees Celsius. And then you do the adding of the salt. So here you have water plus NaCl. The boiling point of water plus NaCl is somewhere around 105 degrees Celsius. It takes longer for water to boil if you add salt. That's contrary to everything you know, right? This is the reason. If you have to get your temperature only up to 100 degrees, that's going to take less energy than getting your temperature up to 105 degrees for boiling. This takes longer. The reason we add salt is twofold. The first is to add flavor, because anytime you cook a substance in a solution, that substance will usually take on the flavor of whatever you put in your water. The second reason that you're adding the salt is so that your noodles will cook faster. If they're cooking in a solution that's boiling here at 105 degrees Celsius, that's significantly higher, that's 5% higher than this boiling point here. That means that theoretically, your noodles should take 5% less time to cook down. Sometimes your box will tell you to add salt and it'll give you an exact amount of salt to add and an exact quantity of water to be boiling. This is so that you have the exact proper ratio that they found gives you the best flavor and gives you the exact cooking time for either al dente or soft noodles. So no, adding salt does not make water boil faster, it makes water boil longer. The third colligative property is a little bit convoluted. It's more convoluted because it doesn't have as good of a real-world application as the first two properties have. Okay, so let's just define what vapor pressure means. Vapor pressure is basically the same as saying how readily a substance evaporates. If something has a high vapor pressure, I'm going to abbreviate P for pressure, capital P for pressure. It means that it evaporates readily. Can you think of anything that really evaporates quickly? Like if you spill it, sometimes you won't even have enough time to clean it up, it evaporates right away. Gasoline is one of those things. It has a pretty high vapor pressure. Nail polish remover is one of the most one of the things that has the highest vapor pressure. We sometimes call that volatile. I'm going to write this word down. And I spelled it wrong. I apologize. Volatile. A substance in chemistry that's volatile is something that has a very high vapor pressure. It doesn't mean something explosive. Sometimes we hear that word in the common lexicon and we say, oh, that person's really volatile today, or gee whiz, that's a pretty volatile situation, meaning explosive. That's not the correct usage of the term in chemistry. Volatile just means that you have a high vapor pressure, or in other words, you evaporate quickly. Another something that has a high vapor pressure are the compounds that make fish stinky. So when you have fish, you can really smell that fragrance coming out of the fish. Some people care for that and others really don't. The reason why that's so odoriferous, or it smells so strongly, is because it has a very high vapor pressure. The compounds in onions and those other potent foods like onion and garlic, they have a lot of sulfur in them, and that's what makes them volatile, and that's why you really smell it. And it's so volatile that you can actually feel the gases coming up and getting in your eyes, and that's what makes you all weepy when you cut onions. That's because the onions have compounds that are volatile. Okay, so when you have a solution, let's see here. You're going from solvent to solution. Your solvent might have a high vapor pressure, but your solution will have a lower vapor pressure. A good example of this would be any kind of alcohol. Now, I'm not talking rubbing alcohol, I mean booze. The alcohols that have the most percentage alcohol per volume content are the ones that are the most volatile. So we'll just say the more you guys are all adults, so I don't have to worry about you not understanding this terminology. The higher the proof, the more the booze is pure solvent. That's ethanol. Ethanol is the alcohol that makes you drunk. So the higher the proof, the more the booze is pure solvent, the higher the vapor pressure. Okay, let me say that again to clarify. So if you have a booze like 151 is that's one of the highest proof liqueurs you can buy. 151 proof, if you divide that by 2, so that's about 75.5% alcohol. That's about the highest percentage of alcohol you're going to find. The higher the percentage of pure solvent you are, the higher your vapor pressure is going to be. Okay, well, why does that matter? Who cares? Well, when my brother turned 21, my folks bought him a bottle of Grey Goose vodka, the really expensive stuff, and they have a ceramic tile on their floor in the kitchen. Craig is a very clumsy, big fellow. He's 6'8", and you know how it is when you're big. Well, he spilled it on the floor, or he dropped the bottle on the floor, it shattered. Grey Goose vodka everywhere. Before he even had a chance to lap it up, it was gone. It just evaporated. It's a pretty high proof of vodka, has a very high vapor pressure. If, however, he had been able to mix a drink before he was able to break the bottle, like let's say he poured a couple of shots into a glass and filled it up with orange juice or something, because it would have been less pure solvent or less alcohol, it wouldn't have evaporated as readily. Notice this one is a little bit trickier because there's not as good of a real world example. And the final colligative property is that of osmotic pressure. Okay, so why is this important? Well, osmotic pressure is something that's rather unique in relation to the other colligative properties because it actually has applications to your clinical profession. Okay, so if you take two solutions and you separate them by what's called a semi-permeable membrane, and in other words, the semi-permeable membrane allows some things to pass through but not everything. And in cell walls, the something that is allowed to pass is water. And that's about all. Okay, so if you separate two solutions, I'm going to put 4 X's. Every X means one little solute particle. And here I'm going to put a lot of solute. So this side is the more concentrated side. If you have two solutions separated by a semi-permeable membrane, water will flow in between the two solutions in order to equalize the concentration. So which way will the water flow? The water is going to flow from left to right. This is what I want you to write down, tattoo it on yourself, put it someplace where you can have easy access to this. This is very important. Water flows from areas of low concentration to high concentration. Why? To equalize the concentrations. The water is going to try its best to move over here so that it can try to space out some of the solute. So the water is going to leave this side, and if this were a cell, it would shrivel up and get very small because its water is leaving, while this cell is going to expand to accommodate the new amount of water that's flowing in. This cell shrinks, and this cell expands. Okay, so let's talk about why this is important. I'll give you an example. My little boy, who's 3.5, knows that when his fingers are pruny, it's time that he's clean. It's time to come out of the bath. So your example for osmotic pressure is pruny fingers. Okay, so what does that mean? Okay, so you are taking a tub, and this is great because you're relaxing, you're not even worrying about your chemistry, and here's your hand and your feet. Okay, inside the tub, there are all sorts of things. There's a little bit of dirt. There's a little bit of oil, you know, the oils from your skin, the dead skin cells that fall off, the little dirt. Maybe there are a few toe jams in here. That sometimes happens. And then there's the soap particles. That happens too. Maybe there's a rubber ducky. All sorts of things. The concentration in your water the tub water is high. In other words, lots of solutes. at the outset I said that it doesn't matter what the identity of the solute is? In this case, you've got TOGMs as your solute. That doesn't make any difference, but you have to know that they're there. Okay, so you have lots of solutes in your water. Well, you also have cells in your hands. And inside your skin cells, here's a skin cell, you have a small concentration of solute. Remember which way water flows? Water flows from areas of low concentration, small concentration, to areas of high concentration. So your brave little skin cells are going to think that they can try to equal out the difference in concentration between all of your little cells and the tub water. So the water is going to flow out of your hand cells, your skin cells, and into the bathtub water. Firstly, it's dehydrating you because you're losing water to the bath water. And secondly, your skin cells are shrinking. That's what gives you pruny fingers. There's a fancy word for this, and even my 3-year-old knows this. So if you don't know this, you are not smarter than a 3.5-year-old. The word for this is osmosis. Osmosis is the flow of water. Flow of water from low to high concentration. Okay, so we can actually calculate how the water is going to flow between exact concentrations of solutions. This is what's important for you as nurses because this will help you to know what's happening in a patient's blood cell when they're getting an IV of 5% dextrose or glucose as opposed to an IV of 0.9% glucose. Okay, so we're going to always calculate the osmolarity first. Even the term osmolarity sort of sounds like that osmosis. That'll help you to keep those two concepts together. Okay, so the osmolarity of KBr is 0.12 times 2. There are two particles here, K and Br. So that's 0.24 OSM. And what's the osmolarity of 0.12 glucose? 0.12. So which way is your water going to flow? Water flows from low to high. Low to high. Alrighty, let's calculate the osmolarity for this compound. Magnesium sulfate is a common drug that's prescribed. There's one of these and one of these. Sulfate does not get broken apart. That's a polyatomic ion. So our osmolarity here is 0.60. And on this side, it's going to be 0.90. Which way does your water flow? From low to high. From left to right. Okay, let's talk about what's happening now within these actual cells. So pretend that the red circle is a red blood cell. And pretend that the outside circle is whatever sort of drug you're administering. What's going to happen to the cell? Okay, so here we have an osmolarity in this cell of 0.30, and here the osmolarity is 0.15. So which way is our water going to flow? Water flows into the cell. The cell will expand. Okay, your OSM here is 0.30. Your OSM here is 0.30. Which way is your water going to flow? If your osmolarities are exactly equal, that means you have an isotonic solution. There will be no net flow of water. this is how I want you to write it. No net flow. Water is going to flow across that membrane because it's allowed to. But it's going to flow across in exactly the same proportion. It's going to flow in the same amount that it's going to flow out. So it'll be exactly equal. So you'll see no net flow. It would be like if you got paid $10 and then you spent that $10, you would have no net income because you spent it, but both transactions would appear on your bank balance. Okay, now I want you to answer these two questions, and if you can tell me what happens to both of these two cells and send that to me in an email by Sunday at noon, I will give you 2 extra credit points on homework number 4. I think that's